The next point is how to add a straight line that will fit the point. So sometimes when you want to assess the linear relationship visually, you would like to make the straight line that will fit the points. Okay, we will talk about this in particular in the second video. So now it's just a very quick solution. So first you need to make a plot as well. Height data equal to d. I will make a simple plot without any colors. Then if you want to add a line, you have a function AB line that can add a line with any slope and any intercept. Okay, the point is that you need to know the slope and intercept, but you can use another function that will find it for you. It's a function LM, it's called linear model, that can fit a straight line to the points. So we just use the same formula as for the plot. Height data equal to d. Then it will add a line. That's the line that fits the points best. Okay, and because it's just a line, you can change the color of this line. We already did it for the vertical and horizontal line. You can change the type of this line and so on. Okay, so that's how to add a straight line that fits your data points on the scatter plot. Now let's discuss how to calculate covariance and correlation. Well, there are certain functions that does everything for you, and first of all, it's a function cov and cor. Okay, so if you want to calculate the covariance, you just use covariance, and then specify which variables you want to calculate the covariance for example, height and weight. Okay, so this is the covariance. You can see. Let me show it. Show CV. So that's the covariance, 146.6. Okay. Then you remember the covariance depends on the units, right? So let's change height from centimeters to meters. So we will just divide it to 100, and then you can see that the covariance in this case 100 times smaller. So that's exactly the same effect that we have seen in the lecture. Okay. So instead of the covariance, you can calculate the correlation, which is normalized, which is unitless, does not depend on the units, right? So that's the correlation. Then show R. Then you can see that the correlation is 0.96. So we have a pretty strong correlation, very strong correlation between height and weight. And then if we, for example, divide height to 100, so if you calculate correlation for the height in meters, the value is absolutely the same. So correlation does not depend on units. Correlation only depends on covariance, how the variables covary. Okay. If you have a data with many different variables, you can calculate correlation for all of them simultaneously. Okay, because we have 12 variables, it's a little bit too much. Let me make a subset, a smaller subset, where I will keep only 6 variables. Okay, so I'll take a subset. I'll just make it in an easier way. I think I will just use DA, and then columns from 1 to 6. Okay, so this will be my subset. I'll just show it. Let's use head. Okay. So this is my subset. So I have height, weight, hair length, shoe size, age, and income. Okay. So now if you call function cor for a data frame, so instead of providing 2 parameters, the 2 vectors, I provide the whole data frame, it will make a correlation matrix that will look like this. So now I have a, let me just make it wider and run it again. Now I have a correlation matrix. So I have all my 6 variables as columns, and I have all my 6 variables as rows. And then the correlation coefficient is in the intersection. For example, what's the correlation between shoe size and age? That's the correlation between shoe size and age. At least this is the correlation we observe in our sample. Okay. Then you can see that the correlation for diagonal is 1 because it's a correlation between height and height, weight and weight. Of course, it's 1 because all points will lie on a straight line. And then you can see also that this matrix is symmetric because correlation between weight and shoe size is the same as the correlation between shoe size and weight. Okay, and then actually you can visualize this correlation pattern by using a special package which is called Lattice. Let's install it first. So I install this package first. Yes, and now this package has a very interesting function that visualize any matrix as a set of red squares or red rectangles. Let me show you that. The function is called level plot. I need to load the lattice first, right? So library lattice. Then the function is level plot. And then you just provide this matrix with the correlation coefficient. Okay, so look at this. So this is our rows, this is our columns. And you can see that the intersection between columns and rows looks like a rectangle with a fillet color, right? And this is the legend for the color. You can see that if, for example, it's a sign like this, so the correlation is 1. So we can see that all these correlations is close to 1. This is very close to 1, close to 1, close to 1. This is a little bit smaller. You can see it's not a very bright sign. If you have magenta color, then the correlation will be -1. So you can see, for example, hair length and weight almost -1, shoe size and hair length almost -1, and so on. Okay. Then if the color is like almost white, then you have almost no correlation, like we have it here and here. Okay. Then we can use this, for example, you can use this level plot for showing correlation pattern for the whole people data. So if I calculate correlation for the whole people data, not only for the 6 columns, and then make a level plot for the correlation matrix. Look, I have now the pattern for all values. So I can take, for example, I know, IQ, and see if IQ correlates with anything. So IQ and height, it looks like this one, right? This is the color. So it's about 0.1, which is no correlation. Okay. IQ and weight, it's 0. IQ and hair length is 0. So you can just follow the correlation pattern for IQ. Okay. And then you can see that shoe size, weight, height, and hair length, they have a correlation. Pretty high correlation. Some of them are highly correlated positively, some of them are negatively. Of course, in this case, hair length is just -1 and +1. We can't use this correlation coefficient correctly. Okay, but it gives you an idea that you have an association between these variables. So it gives you an idea what you have to investigate further. Okay. Then the next point is, you remember that when every time you calculate a correlation, it's a correlation for a sample. So if you want to know if you have the same correlation for the population, you have to make an inference. We already know that we can use this Fisher formula to calculate the confidence intervals and actually the p-values, but in R, there is a built-in function that does everything for you. Okay, so the inference for correlation. And the function is called core test, so I'll use the same variable R, core test, and then you specify the 2 vectors. For example, let's take the correlation for height and weight, dollar weight. Okay, and then show R. Okay, so I need to run it again. So this is the results for the tests. Okay, let's see that. So you can see it's a Pearson correlation, and then we have, this is the data, and this is the confidence interval for the correlation coefficient. So in our case, our correlation is 0.96. But if we talk about population, if our sample is indeed taken randomly and is representative for the whole population, this is the correlation we should expect with 95% confidence between 0.92 and 0.98. And this is the p-value for a test that correlation is equal to 0 in the population. So it's a chance to get a sample like we have, or even more extreme, if for the whole population correlation between height and weight is 0. And you can see that the chance is 0, strictly speaking. Okay. And then if you want to calculate, for example, confidence interval for the larger or smaller confidence, you can just change the parameter conf level, which you already know from the t-test. For example, if we want to be 99% sure, if we want to make our confidence level 99%, that's the confidence interval for 99%. So it's between 0.80, it's almost 90, 0.90 and 0.98. Okay. So that's how it works.